This is lab 3 on black hole and orbits. The purpose of this lab is to observe the motion of an object due to gravity. In part 1, we analyze the motion of a star to find the mass of a black hole, and we see the mass to be 1.12 times 10 to the 34 kilograms. And in part 2, we examine the relationship between three bodies in motion. And to get a unique orbit by the spaceship, we had an initial velocity of negative 12,000, 38,000 meters per second. And so the models and principles we used were the closed-grip computational model, Newton's second law, the momentum principle, perpendicular and parallel forces, and then Newton's law of universal gravitation. So these equations turn out to be F net over mass equals acceleration, the velocity update, position update, universal law of gravitation, and of course our different forces in parallel and perpendicular. So our initial conditions for part 1, we had the system was a star, surrounding was a black hole, and we were given the mass of the star in delta T. And then part 2, our system was a ship, and its surroundings were the planet and the moon. And we were given the mass of planet, moon, and ship, and velocity of moon, and then we were able to set the initial velocity of the ship. So in the experiment, we calculated the parallel and perpendicular forces using dp/dt equations. Then found the mass of the black hole by solving for m in force of gravity equation. So we looked at the forces on the star and worked in reverse to find the total gravity. And then in part 2, we calculated forces for each object using universal gravitation, so that is the moon and the ship. And then we updated the moon and ship velocities and positions. And then we used trial and error to find an orbit demonstrating effects of both planet and moon on a ship based on the initial velocity. And so we go to our code here. We can look at the first one. We update our different components, so our momentum and our change in velocity and change in momentum. We find our different forces in the parallel and then perpendicular directions, showing the relationship of each. And then we take the average of our black hole mass, and when we run it, we can see the different force vectors. So orange is the F net, blue is always perpendicular to the parallel force, which is the pink one, and that is sometimes in the direction of motion or opposite, and this is always pointing towards the center of the circle. Then so we go to the second one. There's our final one before we move on. Here's our second one. This would be the end result model, but when we run it, we had to find, here are our initial velocity from those two parts, and we found the different radius between the things, and then universal gravitation, same for that. We did it 4 times to show the relationship between each object. Then we update the velocities and positions, and when we run it, we can see how it's more affected by the moon in these situations, and then it gets taken over by the planet. And then in a little bit, when the moon and ship align right in this area, it'll carry on with it to about here and then keep falling, and we'll wait for that to happen. But yeah, this is a unique orbit that we see. It'll happen right here, it follows it, and we can see a unique orbit where the ship is both affected by the moon and the planet. And then so we go on to our comparison errors. This is strictly computational, so it's all theory based, and so the only possible error that we could see would be in the code, and we're just looking at how to find different values based on given initial values. But this is actually a realistic launch speed considering the initial conditions and if we were in space. And then some of our reasoning and conclusions: we can find the mass of an object and its surroundings can be found from knowing initial momentum of the system when in motion due to gravity. And then our small body can interact with both planet and moon to create unique orbits. And so the rate of change of the momentum is the same as the net force, and it is true for the parallel and perpendicular components as well. However, the rate of change shows how parallel affects speed while perpendicular affects curve. And then if a system had a black hole, star, planet, and a moon, you would need to look at force of gravity by each one on the others except for the black hole. The black hole is too massive to be affected by the others due to gravity, and so the black hole's influence on all the others would be much greater unless an object was close enough to be bound by one of the others. So the moon could be bound to the planet, or the ship could be bound to the moon, something like that.